So section 10.7 is vector functions and space curves. So we'll start to talk about how general curves might be defined in three-dimensional space and a little bit of two-dimensional space, just to review some of that. So a vector valued function in R3 has the given form below. R of t, some vector r, described by its components x of t, y of t, z of t, or written in terms of standard basis vectors I, j, and k, where t takes on any set of real numbers within, or any subset of the real numbers, called the domain of the function. So the first example we're given here is we're asked to describe the curve given by r of t equals negative sine of t, cosine of t, t, for t greater than 0, and describe its projections onto the coordinate planes. So let's work through the steps of that. We decompose the function's vector components. The x component is here, y and z are here. We notice that x being equal to negative sine of t, that's just a sinusoidal wave function. Same thing for cosine of t. And z equals t is just a linear function, a line passing through the origin. So that's essentially the coordinate plane projections. Now, if we look at, or it gives us some description of the coordinate plane projections. Now in the xy plane, what we think about doing is just shutting off a variable. So for the xy plane, we would set z equal to some constant, really maybe just eliminate it altogether and think about it in terms of two dimensions. So in our xy plane, we have negative sine of t, cosine of t, which if you recall from Calc 2 is a circle of radius 1. So we've got that. The xz plane, we shut off the y variable. Negative sine of t and t, that's a sinusoidal wave. That's the parametrized version of y equals negative sine of x, where x is equal to t and y is equal to negative sine of t, or vice versa, with the roles of x and y there. In this case, we are talking about x and z, so that's the xz plane. Again, that wave has amplitude 1, and then the yz plane is cosine of t, t. So again, this is the parametrization of a function y equals cosine of t or cosine z, where z is equal to t and y is equal to cosine of z, and that would be our standard Cartesian representation of that versus this parametric representation. Again, that's a sinusoidal wave with amplitude 1. So what we see in different slices here, if we look down along the z-axis, we see a circle. If we look at it from side to side, we see two different sinusoidal waves. And what ultimately this curve is, if we imagine it here, it starts at the origin, or not quite the origin. Y is equal to cosine, or y is equal to 1 when we have a 0 in there. So y is 1. So it starts here. And it's a helix moving up the z-axis. So if you look down the z-axis, you see a circle. And if you look at it from the sides, either of these planes, you see sinusoidal waves. And that's this curve. Not all curves are easy to discern. So we won't always try to identify every curve in these terms, but we can always break things down in terms of their components. So let's see what's next. The curve r of t is equal to 3, 13 cosine t, 13 sine of t. It's a circle. It says to find its center and radius and find the plane containing it. Okay, so we'll focus on this portion. This is why this is a circle. So this is actually a circle in the yz plane. We just note that in two dimensions, 13 cosine t, 13 sine of t, is a circle centered at 0, 0 with radius 13. So the last thing we need to figure out is where the center is. Well, it's centered at 0, 0 in this plane, and we know that the x-coordinate is fixed at 3, so the center of this circle is at 3, 0, 0, and we already know the radius of 13, so that completes that problem. So again, we kind of shut down or just ignore one part of this vector expression, especially if it's a constant, and it gives us some idea of what the curve that we're dealing with is. Next up, find a parametrization of the line through the origin whose projection onto the xy plane is a line of slope 3 and whose projection onto the yz line is a line of slope 6. So we'll assume when they say xy that y is equal to 3x would be a line that would satisfy this, and for the yz, z would be equal to 6y, just for the dependency order in the xy plane and the yz plane that's implied. X comes before y, so x must be the independent variable. Same thing with y and z listed in this plane here, the yz plane. So then we know which order, how to put these relationships together. So y is equal to 3x. Let's go ahead and set our parameter x equal to t, y equals 3t. So that gives our parametric equations. Same thing we would do in Calc 2 or in a trig class. And for the yz plane, y is dependent on z. Z is equal to 6y for our Cartesian curve. And then parametrizing this, let y be s and z be 6s. Ultimately, r will be equal to t. X will just be the free variable t. We declare that here. Y is 3t. And z is, well, 6 times y. Since y is 3t, we have 6 times 3t. Our final answer is t, 3t, 18t for this line. Okay. So it's a sufficient finish to that. Parameterize the intersection of two surfaces, of a surface and a curve. Okay, well, two surfaces actually. This surface, if we look at it and realize that's a circle in 2 dimensions, so in 3 dimensions it's actually a cylinder, right? That z variable is free to take on any value it likes, so it extends up and down along the z-axis along this circle in the plane, in the xy plane. That circle has radius 2, centered at the origin, by the way. Now, the other curve we know less about. We could probably classify it as a quadric surface, but it's not really necessary. The trick to this problem is to use the trigonometric parametrization of x squared plus y squared equals 4, or really any parametrization. But if we do that, realizing that this is a circle of radius 2, then we know that its parametrization is c of t, which is 2 cosine t, 2 sine of t. And then we have substitutions for x and y. X and y are 2 cosine t, 2 sine of t respectively. So we take our equation, the other equation, and it's going to become, just substitute our x and y values into this. So now we can solve for z in terms of t, and we end up with this expression right here. So z is equal to 4 cosine t squared minus 4 sine squared t plus 1. And we're actually missing a little bit of information in this problem. We need the rest of the components. So let's add those in. We already know what the other components are, but we don't need to know z. We don't need to write z explicitly. This is going to be in a vector notation. So completing this, we'll have, we've already found what y was. That was 2 sine of t, or we reparameterized that y component, and x is 2 cosine of t. And that's our full parametrization of the curve of intersection of these two surfaces. And we make a note that t takes on any real number in R. Good. The next one, provide a parametrization of the circle embedded in a horizontal plane with radius 6 and center 2, -1, 4. All right, so the first thing we can pick up on is the fact that this is a horizontal plane, so it's parallel to the xy plane. Okay, so essentially if we look down along the z-axis into the xy plane, we'll see a circle. We won't see the tilted perspective that we have in the sketch of it right here. So that gives us that much. We know that this circle needs to be defined in terms of the xy coordinates. So that gives us the first part, 6 cosine t, 6 sine of t, gives us a circle with radius 6. The problem with this circle is it's centered at the origin. So to fix that, we need to shift it. We need to shift it so that it is centered at 2, -1 in the xy plane. Z is not playing any role in forming this circle, so we just fix Z as 4. Okay, so cleaning all of this up. Well, to shift a circle in parametric equations, all we need to do is add that +2 to change our center from 0 in the x-coordinate to a +2, and then subtract 1 to change our center from 0 to -1 in the y-coordinate, and we'll have exactly the center that we're looking for. This is different than what you do for Cartesian curves. Remember that shifts usually are opposite signed. So you double check that this makes sense for parametric curves. So beginning a little bit of calculus with these vector functions, we'll define the limit. Once we have the limit, that will define the derivative, and then once we have, the limit will also define the integral, or the Riemann sum of vector functions. The good news is, this is all very similar to one-dimensional calculus, except that when we take the limit of a vector function, well, we'll take the limit of each of its components. And well, this was only true if each of these limits exists. So it's the standard rules with limits. The identity here works. This is equals, it's truly equals, if each of the limits on the right exists. That's the case. The limit on the left exists, and we're all set. We do things as we normally would. So below, this example should seem somewhat familiar. We have a limit of this vector function as t approaches 1. So we take the limit of each of its components. A little bit of work needs to be done for some of these. The first one needs to be factored to cancel out a common factor. We find that limit as t goes to 1 of t plus 1 will be that component. This one's straightforward. The function's continuous at t equals 1, so we're able to plug in t equals 1 directly. This requires L'Hopital's rule. So we see an execution of L'Hopital's rule here. These two limits are equal as long as this one exists. Turns out that one exists. So it was correct application of L'Hopital's rule, and everything finishes up nicely to be this vector here. So it's just the same calculus you've always done. It's just you do it for that many more components when we're dealing with vectors. Next is to see derivatives. Derivatives will work in very much the same way. We should note that the definition is just a little bit more involved. We will calculate this limit of a vector function so that what we saw on the previous page is actually when we carry out a derivative, what's actually happening is we're taking the limit as t goes to, or as h goes to 0 of, this would be x of t plus h, y of t plus h, and I think the reader, or the viewer sees the point of this, z of t plus h. Essentially, the derivative is just doing the derivative in 3 different components, taking that limit in the 3 different components that are here. And I'll put ellipses to show that that's not really a finished comment, but it starts you off on what the deal is. But otherwise, everything is exactly the same as single dimensions. You're just doing it in each of the 3 components. Compute r prime and r double prime. Not a very difficult problem, especially given that we can easily find the derivative of these functions. R prime turns out to be the first line. Pretty straightforward power rule for all 3 of these components. Leaves us with this, and then take a derivative of the first derivative to get the second derivative, and those are the 3 components of the second derivatives vector. Now, chain rule, product rule, these things can come into play as well. So not quite for dot products or cross products yet, but we can look at a vector function r of t and a scalar function f of t. We can multiply a scalar times a vector, so we can multiply a scalar function times a vector function. This is exactly what they're asking us to take the derivative of below. Now, the point of these exercises is to show that we can split this up as the derivative of r prime of t times f of t plus r of t times the derivative of f of t. Or we can multiply it all out if we prefer, and then carry out each of the product rules that happens in each component. So either way works. It's probably easier to use the outer product rule of just e to the t here. And that's exactly what we've done and what follows. Proving that's pretty straightforward. The book contains probably an example of that or the details of that derivation. So this is the derivative of the vector function times the scalar function plus the vector function times the derivative of the scalar function. And the ending result is that. We could leave e to the t as a factor of each component or leave it as a scalar times the vector function. Just pay attention to what an answer prompt might request of you. Now, the chain rule also exists for these. R of f of t. F of t is a scalar output. R takes a scalar input, t. So of course we can have a nested functions and we can take the derivative of these via the chain rule. So in this case, it looks like we have embedded, well, without much else to do, if r of t is t squared, 5t, and 1, then and f of t is e to the t, then we put everywhere we see a t, we place e to the t, and we'll take the derivative from here. That result looks like the following. So the chain rule is a little bit cleaner, a little bit easier, but it follows exactly as one would guess. Note that there's no f of r of t in this situation. And just to put a note here, f of r of t does not exist. Okay, and I'll let the reader answer why that's the case. Why is there no f of r of t? Think about domains of functions here. Okay. Differentiation rules, well, that brings us to basically a summary of all of these, and we see that there are some nice rules. The dot products, we've seen these three essentially. The dot product has something very similar to the product rule. That's nice. Even the cross product has something very similar to the product rule. Just remember that this dot in these times are very distinct definitions. Those are the vector dot products and vector cross product that we're familiar with. This is our chain rule that we already saw. Above this is our scalar function times a vector function. And this is just linearity of the derivative, splitting it over sums and factoring out constants. This is we've done this quite a bit in the past, so I'll leave all those unaddressed. So some really nice rules for differentiation, and we can use those in the future if needed. So when we continue the next video, we'll talk about the unit tangent vector, this t of t. It's a pretty straightforward calculation. It's a very useful object to know. That'll be part 2 of these videos.